Swayam Prabha. Digital India. Educated India.
I see immediately that Ci in this example is epsilon ijk aj bk. This whole cross product business can be written down in one line like that. You take two vectors A and B, it's got components A1, A2, A3, B1, B2, B3, and I want the cross product of these two guys, it's got to be a vector. So if I write it in tensor notation, if it's some vector C, then C sub I is epsilon ijk aj bk. What are the free indices on the right hand side? I. What's the free index on the left hand side? I. There's only one free index, so what sort of object is this? It's a vector. And where are the dummy indices?
J and K.
J and K. So you have to sum over J and K. And if you write down what is C1? Epsilon 1 jk aj bk. If in epsilon 1 jk, the first index is taken away by 1. So j and k must run over the indices 2 and 3. Because epsilon 1, 1 something would be 0. Right? So this could be either epsilon 1, 2, 3 or 1, 3, 2. If it's 1, 2, 3, it's a plus 1. So this is A2, B3. Otherwise it's minus and it's A3, B2. So this is an extremely simple way of writing down the cross product of two vectors. What is this equal to? There's just one more identity which you need to use. It will be very, very useful. What is this equal to? What sort of object is it? It's a scalar. Scalar. All dummy indices, all indices are summed over. How many such terms are there which are non-zero here? How many epsilon ijk's are non-zero? 6, right. So start by writing 1, 2, 3. The other guy is also 1, 2, 3. And that's plus 1 squared, which is 1. You take all the plus elements and square them, you get 1 plus 1 plus 1. And take minus elements and square, you get minus 1 squared plus minus 1 squared plus minus 1 squared. So how much is that? 6. So this is a number, that's 6. What is this equal to? And this is the most important identity of all. Epsilon ijk, epsilon il. M. What sort of object is this? It's a tensor of order what? Of rank what? Of rank 4. And what would be the free indices on the right hand side? JKLM. So this is called contraction by one index. You contract it with one index and you get a tensor of rank 4. You contract two indices, you will get a tensor of rank 2. You contract all three, you get a scalar. Okay. What do you think this is going to be? What do you think it's going to be? Well, let me write the answer down. I want you to verify it. It's delta JL delta Km minus delta Jm delta Kl. So you have indices Jk, Lm. So J goes with K and K goes with M and gives you a plus Kronecker delta. And then you flip it over, it gives you minus Kronecker delta. The right hand side is a tensor of rank 2, rank 4. What happens if I contract two indices? So what happens if I have epsilon ijk, epsilon ijn? You can go back here and put j equal to m. You get a tensor of rank 2 multiplied by some numerical factor, twice something or the other. When you contract once more, you get twice the trace delta ii, which is 3, and it will give you 6. So work this out. So how would you write a thing like this? How would you write a thing like this in tensor notation? What sort of object is it, first of all? Scalar, vector, or tensor? Yeah, it's a scalar. First you do b cross c, that's a vector, then you dot it with a. How do I write it in index notation? This is equal to ai, b cross c, the I component of it. By definition, that's the dot product, right? But b cross c I is equal to ai epsilon ijk which I can also write as epsilon ijk ai bj c. Very nice and symmetric form. It follows at once from the symmetry of this object, it follows at once that this is equal to C dot A cross B. And you have this cyclic property of the triple product, triple scalar product. Follows immediately. By the way, what is this quantity equal to? A symmetric tensor of rank 3 contracted with an antisymmetric tensor of rank 4. Some crazy combination. We don't even know how many components this has. You've got to work it out. I don't remember now. And this is a symmetric tensor of rank 3. Only L is free. What would the answer be? When in doubt, the answer is always 0. Because if you contract and you interchange in this dummy indices, this will undergo change of sign, which this doesn't. You cancel out pairwise, it will go. Okay. What is this equal to? Sij, Aij. What's this equal to? I and j are dummy indices, so I can interchange them without changing the meaning of this whole thing. So I interchange them. So when you contract a symmetric tensor with an antisymmetric tensor, the answer is 0. Even if the two tensors are different ranks. What is this quantity equal to? You see, this is some kind of universal thing because it's just the element of the identity matrix. This is a universal thing. in 3 dimensions. It's nothing to do with any specific coordinate system or anything like that. But if you want the answer to be a vector, that vector has got to point in some direction. Is there any direction in space that is singled out? Only the null vector is possible, right? So the answer is 0. It's a symmetric tensor contracted with an antisymmetric tensor, totally antisymmetric tensor. So the answer is 0. Okay. What is this equal to? What is this equal to? We can work it out, we can write it in terms of epsilon and so on. You'll get 2 epsilons now because there are 2 cross products, and then you use the formula that of contracting 2 epsilons in terms of delta delta minus delta delta, and then you get the answer. But let's write it out. We'll give you a simple physical argument for what this answer is, right? Very trivial argument. What sort of object is it? It's a vector, right? Definitely a vector. If I multiply A by 6, will the answer multiply by 6? Instead of A, I replace it by 6 times A. Will the answer be also multiplied by 6? Yeah, definitely. Is that true for B and C as well? Yes. So it's linear in A, B and C. It's proportional to A, B and C. What's it if either any of these vectors is 0, what's the answer? The answer is 0. So it's got to be linear. Is it perpendicular to A or along A? Perpendicular to A. So let's suppose these 3 vectors look like in space like this, some axes like that. In general, they are not coplanar or collinear. They are in 3 dimensions, 3 directions in space, arbitrarily. Right? You are guaranteed that this vector is perpendicular to A. But in 3 dimensions, you can resolve any arbitrary vector along 3 non-coplanar vectors. Not a coordinate system which is orthogonal, but you can certainly find the right unit vectors along those directions and make this expansion, because you've got 3 directions. But it has no component along A, therefore it must have components only along B and C. So this must be of the form something times B plus something times C. It has to be. And what's in those brackets? Are they vectors or scalars or numbers or what? They can't be vectors because the vectors are already here. They must be scalars. And what will this scalar depend on? It must depend on A, because if A is 0, the whole thing must be 0. Must depend on A. What else must it depend on? B is already here. B is already here. So it must depend on A and C. What must this depend on? What must this depend on? A and B. So what we must have here is A, B, and this must depend on A, C. And they must be scalars. From 2 vectors A and B, how many scalars can I form? Why? No, I can form A dot A dot B, and B dot B. You can form 3 scalars, right? But A squared, A dot A is A squared. Is that linear in A or not? Not linear, so that's ruled out. B squared is ruled out. So what you're left with A dot B and A dot C. So this must be A dot C, B plus A dot B, C. Must be of this form. But who told you that its coefficient is 1? I could have had square root of pi, or e to the x, a to the pi. I could have had any constant there, any number. Right? Nothing to stop me, any numerical coefficient. Lambda times this. This could have been some other numerical coefficient, mu times that. What can we say about lambda and mu? They are numbers, they are scalars, but what else can we say about them? Will they depend on A, B and C? No, because the dependence on A, B, C is gone completely. What happens if I exchange B and C in this formula? I exchange B and C, what happens to B cross C? Minus, right? So if I write that same thing out, A cross C cross B must be equal to lambda times B and C are interchanged. So this is A dot B C plus mu times A dot C B. I've interchanged B and C and I get this new formula with the same lambda and mu. But this guy is minus this original number. So this must be equal to minus lambda times A dot C B minus mu times A dot B C. This must be true for any vectors A, B, C as an identity. What can we say about lambda and mu? Lambda must be minus mu. That's all you can have. So we have our grand formula. Mu must be minus lambda. So this is, you can erase all these things. We are almost there. What's the value of lambda? Well, you already know the value of this triple cross product from elsewhere. So what's the value of lambda? Are you familiar with this identity? Yes or no? No. This identity is valid with lambda equal to 1. The value of lambda is 1. We are almost there. We need to establish that it's equal to 1. How would you do it? Notice I did not do any vector multiplication. I didn't mess around with any epsilon symbols or anything like that. I just gave a physical argument based on linearity plus what are the possible scalars you can form. Nothing more than that. Plus the fact that a cross product of vector A with any other vector is perpendicular to A. So how will I find lambda? What would be the general strategy for doing that? You've got a general argument which has given you a certain simplified version, but there's an undetermined constant in it. How would you determine the special constant? You'd look for a known case. This is true for any A, B and C. What is I cross J? K. And J cyclic order, right? So I would choose one of the vectors to be I, and this is I, this is J. So you'll get I cross K, which is minus J, and this is I. So you got minus I cross J, which is K. So put that in here. Put in those guys. The dot product of I dot J is 0, I dot K is 0, and so on. Okay. Was that hard or was that easy? But it gave some general lessons on how you think. Okay. Use the same argument, general argument, to do the following. Simplify this. Four different vectors A, B, C, D, arbitrary vectors, and you've got this vector product A cross B, a vector product C cross D, and you're taking the dot product. So will the answer be a scalar or a vector? Scalar. Does anyone remember the answer for this? So use the same argument. The answer must depend linearly on A, B, C, D. It must be a scalar. Form all the scalars possible from these 4 vectors. What are all the possible scalars? Linear in each of the vectors. You have A, B, C, D, 4 vectors, so you have 6 possibilities. A dot B, A dot C, A dot D, B dot C, B dot D, and C dot D. And the answer must be linear combination of those guys, 2 at a time. So don't do any hard work, argue along these lines, general lines. Never do work when you can avoid it. But you have to think. I thought of doing relativity, but we ended up doing vector analysis. Okay. Anything else? I don't want to talk about relativity today. It will take too much time, but another occasion. Yeah.
Okay, my question was actually about relativity.
Okay, no problem.
Why exactly do we consider space to be three-dimensional? Because the math works for any higher dimensional space. So why is space three-dimensional particularly? What is special about it?
I wish I knew. You figure out why you're headed for Stockholm and the Nobel Prize. We don't know. We don't know. There are a lot of very, very peculiar properties of 3 space dimensions which are not shared by higher dimensionalities. And as you know, in string theory, it's believed that the universe was started off with a larger number of dimensions and then they got compactified, etc. So those are speculative arguments. But 3 dimensions have very peculiar properties. And my answer is not going to address the question of why we are in 3 dimensions, but one thing I can say is the following. If you are in one space dimension, there are no rotations. It's too simple. 2 space dimensions has a rotation, but it's just in about one point, right? And in 2 dimensions, you don't have the possibility of knots. Nothing can be knotty. You have something called a braid group, but not knots. In 3 dimensions, you have knots. In 4 and higher dimensions, as you go up the space dimensionality, matters become more simple than complicated. So higher dimensional topology is actually simpler than topology in low dimensions, and the hardest of all is 3 and 4 dimensional topology. So in a sense, in a very vague sense, an adequate amount of dynamic complexity needed to form a complex universe seems to be possible only in 3 dimensions for various reasons. Okay. It's also got another very interesting property. If from the origin at t equal to 0, you emit a delta function, a pulse of light, an instantaneous pulse of 0 width, etc., it spreads out in a spherical shell. It reaches any arbitrary observer as a delta function signal only in 3 dimensions in free space. In higher dimensions, it reaches with a distortion. So the business of intelligent communication seems to be possible only in 3 in this sense. That you must know when a pulse starts, when a pulse ends, so you know when the message starts, when the message ends, without distortion. That peculiar property exists only in 3 dimensions. Besides, in 3 dimensions, you have the possibility that the cross product of 2 vectors is a vector. Electromagnetism is a possibility. It's got a simplest form in 3D, etc., etc. So there are all these vague reasons, but they're not, mathematically rigorous reasons as to why. But it looks like it would be very uninteresting in other dimensionalities. Yeah.
So I also have a doubt in time dilation phenomena. When we consider a person as a frame of reference and another body is moving with some velocity close to the speed of light,
Yeah.
which is comparable to the speed of light,
Okay.
then only time dilation is prominent.
Yeah.
So for time, the clock on the moving object flows slower than the clock having whom we are considering to be stationary, the frame of reference. So if we consider the object which we considered before as moving as the frame of reference, the object which
Yeah,
we
you're
now
saying if it's moving at uniform velocity, these two are symmetric.
yes,
A moves
but
uniformly with respect to B, B moves uniformly with respect to A. Therefore, according to B, the clock of A should be slower, etc. This is quite true, but the point is, as long as you don't introduce acceleration, this is true. But the twin paradoxes that you're heading for involves acceleration. So for a person to go from the Earth to Interstellar or wherever the movie is, took you to, and to come back, at some stage he has to stop and reverse his motion and come back. So an acceleration is involved, it's no longer an inertial frame, and this asymmetry gets introduced. Therefore, the person who went out on the travel and came back will age much less, and so on. It's very convenient to do the following, and this is something that Ghanshyam forgot to mention, I guess, which is the following. You start with an observer, and let's suppose this is space and this is time. Let's suppose there's only one dimension of space, because I can't draw a four-dimensional cone here. So one space, one time dimension, and I have an observer here. At t equal to 0, he flashes a beam of light along the positive x-axis. What is it going to do on this space-time diagram? If you plot Ct here, so that it's got the same physical dimensions as length, as x for instance, then it's going to go along the 45-degree line x equal to Ct. Suppose at t equal to 0, he sees a flash of light coming from minus infinity along the x-axis, that would have traveled along like this. If he flashes the light in the opposite direction, then it goes like that. And if it came from the past, it would be this. So for this observer, O, this is his entire past, and this is his entire future. He has no causal connection with what is going on here outside. This is future, this is past, this is called the light cone, and this is everywhere and everywhere, anywhere else. Because in this case, you can see that c squared t squared minus x squared is the interval squared, and this guy must be positive or 0. If it is 0, it's light. If it's positive, then the t dominates, and that means objects are moving with speed less than c. So in the same picture, if I were to ask, what would the trajectory of a ball be if this observer at t equal to 0 throws a ball to somebody standing on the x-axis, standing there. I throw a ball to him, and let's say at uniform speed, and he catches the ball. What would happen? I am here, and this is O, and he's sitting here, and this is my light cone. That's how light would have traveled. How would the ball travel? It's traveling at a speed less than the speed of light. So the slope of this trajectory cannot be less than 1, because this is Ct. Because light itself, the slope is 1. It's got to take more time to travel a shorter distance. Therefore, the slope is greater than 1. And this ball would go like this. And this fellow here, the other observer, meanwhile is standing here waiting for the ball to reach him, and meanwhile he is not static, he is not moving in space, but he is getting older. So time is elapsing for him, and they are both in the same frame of reference, and he catches the ball over there. And he throws it back, and I catch it back here at some time, etc. If I throw a ball up, forgetting air resistance, forgetting friction and so on, I throw a ball up, the ball slows down at the top of its trajectory and comes down. What would the space-time diagram be like? So let's suppose this is the vertical direction z, and this is Ct. And that's the light cone. What would throwing a ball up and come down mean? You see, the ball leaves my hand and slows down and reverts and comes back like that. At this point, you have only dt and no dz. So dz over dt is 0, which means that the ball's velocity upward is 0. It stops and comes down again to me, right? The slope at all times remains greater than 1. At no time can it become less than 1. So when you have complex events, it helps to draw the space-time diagram always. Okay? Now the whole business of special relativity starts with a postulate and a principle. And the principle, as I once mentioned, was the same as Newton's principle. namely the laws of physics are invariant in inertial frames, rotated frames, etc. But then the postulate says the speed of light is independent of the source and the state of motion of the source or the observer, the speed of light in vacuum. What it means is the following. What it means is completely counterintuitive, if you want to put it that way. I start at the origin and I flash a beam of light, spherically symmetrical, expanding in all directions at t equal to 0. After some time, the wave front would be along on a radius r equal to ct, and it would be expanding outwards in this fashion. What Einstein did was to ask the question, what happens if I flash the light and start running along this any particular direction? Then he expected that this is what would happen. Etc. For the moving observer, these wavefronts would be foreshortened in this fashion and distorted, whereas at the back they would be expanded. And there would be a motion which involves the relative velocity, which includes his velocity along with the speed of light. This is what happens for sound. And what happens when you crash the sonic barrier? You come out of the shell and you have a shock wave which looks like this. You left the sound behind. You've gone faster. And you have two shock waves. With light you don't, because you can't exceed the speed of light, but you can't even hit the speed of light. And to great surprise of everybody at that time, it turned out that the picture in the moving frame was also the same. So even for the moving observer, he would see exactly the same thing. That's what is meant by saying his state of motion doesn't have anything to do with the speed of light, doesn't affect it at all. Okay? Which means that the wave fronts that he is looking at are r prime equal to c t prime in this frame. So what has happened is that c squared t squared minus r squared should be equal to c squared t prime squared minus r prime squared. That's the fundamental equation, a constraint that you have to satisfy. And before Einstein came on the scene, there was only one solution known to this equation, and that solution was t equal to t prime and r equal to r prime. In other words, you had only a rotation of the coordinate axis possible as the maximum transformation, and time flowed at the same rate for everybody from the indefinite past to the indeterminate future. The inexorable flow of time. Before Einstein, Lorentz already pointed this out, but Einstein fortified it. This equation has another set of solutions where t prime is not equal to t and r prime is not equal to r, and those are the Lorentz transformations, which correspond to boosts and so on. Okay? You still have rotations, that's still a solution, but in general there is another set of solutions, and that gives you the Lorentz transformation equations. And the effect of this whole business is that the law of addition of velocities is modified. It's no longer the non-relativistic law at all. So if you have an observer, one observer, and another fellow moving with speed v1 along the x-axis, say, and a third observer moving along the x-axis at v2 with respect to the second observer. So you have an O, O prime, and O double prime. The speed of O prime with respect to O is v1. The speed of O double prime with respect to O prime is v2. What is the speed of O double prime with respect to O? What is this speed? What would you say? You would normally write it as, if this speed is v, you'd write v equal to v1 plus, you'd simply write it as v1 plus v2. Not true. Not true. The correct answer is v is v1 plus v2, 1 over v1 v2 over c squared. That's the correct law of addition of velocities. You can derive the whole of special relativity by saying that the law of addition of velocities is changed to this, and then everything else follows, the Lorentz transformations follow, etc. Now what's the consequence of this? If this is not an observer but light, he shoots a beam of light, then look at what happens. You put V1 equal to C, what happens? V becomes C. V becomes C. So that's in keeping with our postulate to start with. That's the way nature is. It says that when you have collinear velocities along the same direction, the law of addition of velocities is modified in this fashion. You could ask, what happens if I have boosts in different directions? These are called boosts. If this boost is along this direction, but then there is another boost along that direction, what would happen? How would that look with respect to this? And the answer is not a boost alone, but a boost followed by a rotation. If you look very carefully at the movie Interstellar, you will see that they've taken into account these relativistic effects. This is called a Wigner rotation, and it's a distortion of geometry, purely geometrical effect. It's not a boost along. But you can now ask the following question: if this is true, if that thing is true, is there some function of V which is linear, which just adds up when I have successive transformations? And the answer is a little intricate, and that's the reason it took till 1905 to discover it. The answer is the following. You define a quantity tan hyperbolic inverse V over C, you call it Z, and it's got a name for it. It's called the rapidity. Plot a graph of this in a second. Right. And it looks like this. Looks like that. And that adds up. So the rapidity of this guy with respect to this is the sum of the rapidity of this guy with respect to this, and ditto with respect to this. They add up. Now you can understand readily that tan hyperbolic inverse is not one of those very trivial functions which you write down every day in elementary school, and that's the reason it took a long time. But in this region where V is much smaller than C, it's approximately linear, and the world is Newtonian. But when you go to higher speeds, that's not true. And as V tends to C, the rapidity becomes infinite.
Sir, how did they observe that at higher speeds, that the speed for higher, the one traveling at a higher speed is same for the one who observes when he's stationary? Because what experiment did they conduct?
So the postulate about the speed of light is a postulate. Now the question is, what are the consequences of this postulate? What happens next? What are the consequences? The mass energy equivalence comes out, the equations of special relativity come out, the relativistic Doppler shift comes out, the addition of velocities comes out, a huge number of experimental consequences follow, and you can test every one of them. So in the absence of extremely strong gravitational fields and flat space-time, we believe special relativity is the correct explanation of nature. And for the last 110 years, we've been trying to find flaws in it, and there are none. Because in a physical theory, you have to constantly be trying to disprove it or push it to its boundaries, and that's being done all the time.
Sir, for symmetrical, but still for symmetrical, I'm not able to understand how for the guy who's moving, the time is slower for him, but for this person it's faster, while for this person is stationary, this clock is faster.
Yeah, but for the two to come back together to be synchronized, able to synchronize their watches, at some stage they have to decelerate. Yeah, that breaks the symmetry.
So it's not possible to come back.
Yeah. You shouldn't think that when I say that the speed of light is the ultimate speed, you shouldn't think that there are no speeds above that. That's entirely possible. It's entirely possible. No information or material matter or energy or any of those physical quantities can propagate at a speed faster than the speed of light. If I take a flashlight here and flash it on that wall, and I move my arm in a circular path, and I give it an angular velocity, that path, the point is going to move. It's going to move at a linear speed, which is omega times r. Omega is my angular velocity of my wrist, and r is the arm distance. Okay. By making omega large enough and r large enough, I can make that go as fast as I like, 100 times the speed of light. If I have a screen on the moon and I shine a laser beam at it and move it fast enough, it's going to be much faster. But no information is going from A to B at a speed faster than the speed of light. This beam of light, which is just a splash of light there, that moves. It's okay. Or if I take a pair of scissors and cut it, the point of where the two arms of the scissor appear to move can move at any speed, arbitrary speed. Nothing to do with the speed of light limitation. These are not physical speeds. Or for that matter, for every wave, the phase velocity is greater than the speed of light. So that doesn't affect any physics. Yeah.
Sir, what exactly is rapidity?
This is just a name given to this quantity here. It's like the velocity, but it's the complicated function of the velocity, a non-linear function of the velocity. And the historical name given to it was rapidity. It means that the world is such that rapidities add up for collinear velocities, particles moving per point, objects moving in the same direction, but not velocities. You have to give it a name. Pardon me? The rapidities of successive Lorentz transformations or successive boosts add up provided they are all in the same direction. I wrote it as xi, the Greek symbol xi. That's just to show you that I know a little bit of Greek. Well, the first requirement of a scientist is to know Greek. At least you should be able to write unknowns in Greek letters. Well, physics is full of such terms. Natural science is full of such terms. You already heard from Professor Shankar Raman about chirality.
Sir?
Okay. You also heard something called spin. You can ask what's the component of the spin along the linear momentum divided by the magnitudes of these guys. You can ask what is this? This is called handedness, and there's a word for it called helicity. And the generalization of it is called the felicity. So people use fancy names. And in elementary particle physics, you use, for the quarks, you have named them by exotic number names, right? There's an up quark and a down quark. Has somebody talked to you about particle physics yet? That will have 6 kinds of quarks. There's up, down, strange, charm, truth, and beauty. They have nothing to do with those qualities in real life. What's in a name?
Sir, how do we know that do we know why any of this is true?
Good question. That's a good question. It's good to be skeptical. How do we know it's true? Because now he is equating me to one of these godmen who makes assertions and doesn't prove it and so on. So I need to prove all these things, both theoretically as well as by experiment. Due to lack of time, I haven't done that. But I assure you that it's been tried repeatedly. There's no such thing as being able to prove a physical law's truth. You can only find its region of validity to some accuracy. For instance, you know that the statement is made often that a photon is massless, 0 rest mass. How do we know? We don't know. We don't know that it's truly massless. What we can do is to think up clever experiments which will tell you the photon's mass cannot be bigger than such and such a number. And the number that people have found, the best estimates are of the order of 10 to the minus 60 kilos. We know that the photon, if it has a mass smaller than 10 to the 60 kilos or so. 30 orders of magnitude smaller than an electron's mass. But we're never going to be able to prove that's exactly 0. On the other hand, what are the consequences of the photon having a mass? Electromagnetic interactions would have a finite range, depending on the rest mass. Immediately a whole lot of things would change. The whole of electricity magnetism would change. Even the simple fact that in a normal tank circuit made of an inductor and a capacitance, the resonance frequency is 1 over square root LC, even that will change. And you can think of a tabletop experiment to measure this frequency very accurately. The way the photon's mass bound is put on it is by saying what's the Earth's magnetic field do at the satellite, and if it's massless, then there is an inverse square relationship, otherwise it's corrected, and people know that. There are other ways of doing it as well as to what happens to photons when they pass through interstellar matter and so on. So there are tests and checks and balances. There are no authority figures here in science. Every time a great scientist has said in his hubris that after achieving a great deal of things, they say the universe should behave like this, they have fallen on their face. So it teaches us a great lesson.
So you said they're testing to see if.
Pardon?
You said they're testing to see if the photon has mass. How do they test for it?
How do they test for it? The first thing that will happen is that the inverse square law of gravity of Coulomb's law will be modified. So you check whether Coulomb's law is valid or not. And Edwards did an experiment long ago to establish that this law is valid. But there are more sophisticated tests of it which depend on the interstellar magnetic field, the Earth's magnetic field far out in space and so on. There's a whole lot of tests for the photon's mass. Okay. Very roughly speaking, what happens is if the photon has a mass, then the electrostatic potential, which look like R over lambda Compton over R, where this guy here is 1 over the mass of the photon times the speed of light, h over. So its range would not be infinite anymore. Gauss's law would be violated, etc. Gauss's theorem in electrostatics would be violated, etc. Planck's constant. Oh, he's got a good question. What is this H? This stands for tan hyperbolic. I see. Are you familiar with hyperbolic functions? Hyperbola. Well, let me give a nut answer quickly, because what is the definition of, are you familiar with e to the power I theta?
Yes, sir.
Are you familiar with this identity?
Yes, sir.
Cos theta plus I sin theta?
Yes, sir.
Can you write cos theta in terms of exponentials?
Yeah. Yes, sir.
And what about sin theta? This cannot be true. Why can't this equation be true? For real theta, this can't be true. Yeah, over 2i. Because sin theta must be real, but that thing here is a complex number minus its complex conjugate, and that cannot be real. It's pure imaginary. You need to divide by this I. So I can look at cos theta as the symmetric part of e to the I theta, or the real part of e to the I theta. Now I can ask what happens if theta becomes a complex number, pure imaginary. And then you get a quantity which looks like e to the theta plus e to the minus theta over 2. And this is defined as cos hyperbolic, pronounced cosh theta. In exactly the same way, you have sin hyperbolic theta is e to the theta minus e to the minus theta over 2. The even and odd parts of e to the theta. And tan hyperbolic is the ratio of sin hyperbolic over cos hyperbolic. There's only one function. There's only one independent function in this whole business. And what's that? What function sticks out in all this business?
E power x.
Yes, exactly. E to the power z, where z is an arbitrary complex number of finite magnitude. This quantity is defined as summation n equal to 0 to infinity z to the power n over n factorial. It converges absolutely for all finite mod z, not necessarily those less than mod 1, less than 1. Converges for all z. Real, complex, we don't care. So you can differentiate it, you can integrate it term by term, you can do anything you like to it. Okay. And these are all functions derived from it in various ways. This morning Sriram showed a power series for sine theta and cos theta. It comes from this, using this relation. Those are the correct definitions of all these trigonometric and hyperbolic functions.
Sir, in cis theta being e power I theta, the proof involves the Taylor series for cos theta, sin theta, and e power x, sir. So, how do they derive Taylor series?
How did you get the Taylor series?
Yes, sir.
Well, just how do you derive? What's the particular? The derivation part is mechanical. That's not the difficult part. The question is there some intuitive understanding of it, physical understanding of it, and so on? And let me try to tell you what it is in very simple terms. If you have a curve of this kind, some function here, and you want to find its value at this point, some number at that point. If I want to find its derivative, I take values of I take this function at x minus epsilon, x plus epsilon, take the difference. If I want the second derivative, I want the difference of the difference. So I go a little further out, and a little further out, and a little further out. If you want to go a finite distance, you have to take an infinite number of terms, all derivatives. That's your Taylor series. It involves higher and higher derivatives, which takes you further and further out. Hand-waving way of understanding derivatives, but as good a way as any. Yeah. And there's in the whole business of calculus, just like in tensor analysis, there's just one rule you have to remember in this whole business. The power is stronger than the logarithm, and the exponential is stronger than the power. So whenever there's competition between them, the exponential will win over the power will win over the log will win over the log, etc. That's calculus in a nutshell. No, really, seriously, I mean, all the limits and other problems that you get, you just have one principle there. What is 0 to the power 0? What's the limiting value? Yeah, it's 1. It's 1. But how do I get it? Yeah, you write this as, this is equal to e to the x log x.
X log x and log x.
And the limit of this guy is 0 because x is a power and log x is a log. So it's 0 multiplied by minus infinity, but this 0 is stronger than that minus infinity. So the whole thing goes to e to the power 0, which is 1. But it teaches you a valuable lesson. If you have two real numbers a and b, and I want the limit as a goes to 0, b goes to 0, through positive values for instance, then if a goes to 0 first and b remains non-zero, the answer is 0. But if b goes to 0 first, the answer is 1. So when you have double limits to be taken, you have to specify which one is physically relevant to you. And it plays a big role in analysis. No, all I said was this example is one of those things that shows you, for instance, if I have e to the minus x, x to the power n is a positive integer, and I ask what happens to this as x tends to infinity, what would you, plus infinity, what would you say? This guy is dying down very fast, this is increasing, but this wins in the end, and the answer goes to 0 as x tends to plus infinity. Okay. Just as here the x won over the log. You can figure that out by using L'Hopital's rule. You're familiar with L'Hopital's rule for finding limits? Yeah, pain in the neck to follow this rule. You don't need it.
Sir, I had a question about gravitational lensing. You said that photon has no mass. So how can things that have mass affect space? And how can things without mass
It's a
be
good
affected
question.
by space?
The photon is affected by the gravitational field because the gravitational field couples to anything that's got an energy density. And by the mass energy equivalence, it's got an equivalent mass. So it doesn't need physical mass itself, rest mass, but an energy density is sufficient, which the photon has. Then you could ask the question, gravitation itself has energy density. Does it affect itself? And the answer is yes. And that's the reason why we don't have a successful quantum field theory of gravity as yet, because of this self-interaction. So yes, the photon does get affected by gravity. That was one of the tests of special relativity. Incidentally, you all made an assumption in school which is not quite right, because if you go back and look at this equation, F is equal to m times a, let's talk about just magnitudes, and this force is caused on this mass m by a huge mass, capital M, then this force would become equal to g times m over the distance between the two particles, r squared. This is how you work out satellite motion and stuff like that. And what you do is to merrily cancel this out, little m. Same on both sides and so on. But there's a profound assumption involved here. The equation gm on m2 or mm over r squared is specific to gravitation. It's Newton's law of universal gravitation. So this m is the strength with which this little mass m, mass little m, couples to the gravitational field caused by the bigger mass here. It's a coupling strength constant, like q1, q2 over 4 pi epsilon naught r squared. It should be called the gravitational mass. This mass here is the inertial mass. It appears for any force. No matter what kind of force you apply, Newton's law says the acceleration is the force divided by the mass. That mass is the inertial mass. Who told you the two are equal? Just because the writers of textbooks have written the two to be in the same symbol doesn't mean they are equal. They come from two different origins altogether. One is a gravitational coupling constant and the other has got to do with inertia. Why should the two be equal? Now you didn't ask this question in school. I never asked, even less. I never asked this question. Most of us didn't. Einstein asked this question and realized that if you put the two to be equal by postulate, it's called the principle of equivalence, the whole of general relativity falls out from it. So by asking the right question here, he actually understood the nature of gravitation. So don't take things for granted. You have really no business equating these two masses. Now you can ask, can I test this principle of equivalence? And any test of general relativity ultimately tests that principle. And those tests which have succeeded tell us that within the range of physical parameters which you can specify, it is right. This postulate is right. Okay. Yeah, the postulate being that the inertial mass is equal to the gravitational mass. Not at all an obvious statement till he pointed it out. The consequence of that is that in a sufficiently small space-time region, you cannot tell the difference between a gravitational field and an acceleration. They're exactly the same. And it's remarkable that a whole theory of gravitation can be built upon that. So not only must one ask questions, but one must ask the right questions, and that takes people like Einstein to do it. But we can try in our own small way to ask small questions and so on. That's why when students say that they have a doubt, I always, in lighter vein, tell them, you don't have a doubt. You and I have questions, to many of which there actually are answers. People like Gautama Buddha and Jesus Christ and Vivekananda, they had existential doubts. We have questions which we can answer. Sometimes we can answer them. Many times we can answer them.